Hi dear students, this is the 7th part of the 5th module of the subject EST 100 Engineering Mechanics. So far we have seen different types of motions. All the motions are either rectilinear motion or curvilinear motion. So in this presentation we will be dealing with a new type of motion, that is general plane motion. In this motion, both rotary motion as well as the translatory motions are coming together, or we can say general plane motion is a combination of both rotation as well as the translation. A body is said to have general plane motion if it possesses both rotation and translation simultaneously. You can see an example shown here. See, this is the example for the general plane motion. A roller is rolling from the initial position. See, you can see a dotted line. This is the initial position. It has moved to a distant new position. See, A1 is the center of the roller at the initial position, and A2 is the new center of the roller at the final position. So it has moved from this position to this one. During this motion, you can see it has covered. It has there comes two types of motion. One is translation and the other one is rotation. You can see from this figure, see the center A1 is moving to a distance of this much distance and coming to a new position A2. So the motion of the particle A1 to A2, you can consider it as a translation or linear motion. Similarly, the point B1 is moving along a straight line from this position to new position is this one, that is B1 dash. So B1 has traversed the same distance as A1 is did from B1 to B1 dash. So the entire motion from this entire motion shown in this figure is the example for translatory motion. See, each particle is moving a particular distance, then the distance moved is the same. That is the peculiarity of the translatory motion. So this is the example for translatory motion. Now you can see from B1 dash, this point is alone moving along a curved path to a new position B2. See, so the entire motion can be concluded as the movement of the point B1 along a straight line to this position. This position is marked as B1 dash in the right side figure. From that, the point B1 is moving along this curve to a new position B2. So if you consider the movement of the point B1, it is actually it is a combination of linear motion from B1 to B1 dash, and then it traverses a curved motion through this circumference to a new position B2. So this motion can be considered as a combination of this one, that is a translatory motion, plus this one, that is a rotary motion. And one more example I can show you. Here you can see a rod or ladder, anything is kept touching the walls and other end is touching the floor. So it is moving through a particular distance. See, the point B1 which is in contact with the wall is moving to a new position B2, and the point A1 which is in contact with the floor is moving to a new position A2. See, both the ends are actually traversing a translatory motion, but if you are considering the entire motion, this can be split into translatory motion plus a rotary motion. I will explain it. See, the point A1 is moving to a distance A2, and it is covering a linear distance of this much. So at the same time, I am assuming the B1 is also moving from this point horizontally to a new position B1 dash as shown in the figure. So each point of this body is covering a equal distance. So this is an example for translatory motion. Now once it has reached this position, now I am fixing the point A2 and now B1 dash alone is moving along a curved path to new position B2. Now if you combine these two motions, then you will get this one. So every motion of these types are called plane motions. Okay, general plane motion. So in general plane motion, altogether we will have both rotary motion as well as the translatory motion, or it's simply we can say general plane motion is a combination of translation and rotation. Now moving on to the analysis of the general plane motion. Kinematics of plane motion. Consider a wheel of radius r rolling with angular velocity omega and angular acceleration alpha. You can see in this figure the angular acceleration of the wheel is alpha and angular velocity is omega, and it is rotating along the clockwise direction. This dotted line is the initial position of the wheel, and this thick line is the final position of the wheel after time t. Dotted line shows the original position and solid line is the final position after rotating through an angular distance theta. So during this motion, it is covering an angular displacement, angular distance theta, that also is shown in the figure, and radius of the wheel is r. Okay, the linear distance covered is marked as s suffix a, sa. Since there is no slip, no slip means always some point of the wheel will be in contact with the floor. That is what is the meaning of no slip. The wheel will not slip away or lift away from the floor. That is the meaning. Always some point will be in contact with the surface. That is the meaning of no slip condition. Some point will be always in contact. Okay. Since there is no slip, the linear distance moved by this wheel, this is the linear distance BC or A. This distance is the linear distance. So the linear distance moved is marked as SA. So the linear distance moved BC equal to SA must be equal to the angular distance BC. See, actually this is rotating in this direction along the clockwise direction. So what initially the point B is in contact with the floor. Now once it moves in the clockwise direction, what happens is B will be moving along this curve into the clockwise direction. So the new position of the B is shown here, and another point of the wheel on the circumference of the wheel, that is point C, is coming now in contact with the floor. So the linear distance moved, this distance will be equal to the circumference of this one, that is BC. This curved distance BC will be equal to this linear distance. So since there is no slip, the linear distance BC equal to SA. Actually this linear distance BC is marked as SA. So this curved distance BC will be equal to this linear distance. BC will be equal to SA. But actually during that motion, the angular displacement is theta. Now if this angle is theta and this radius is r, then you can calculate this curved distance CB. The radius sector, the curved distance of the sector will be r theta. So BC is equal to r theta. So we can say that since that linear distance SA is equal to BC, that curved distance, and curved distance is given by r theta, and theta should be in radian. Therefore SA equal to r theta. Now if you find the derivative of the distance, then you will get the velocity dSA by dt. D by dt of displacement will be equal to the velocity. So dSA by dt is equal to d by dt of r theta. Since r is constant, it becomes d theta by dt. So this linear displacement by time is the linear velocity. So VA, V is the representation of the linear velocities, A is the suffix, that is the velocity of the point A. VA equal to r omega, this is r, and from the notation, from the fundamental equations of the curvilinear motion, we know that d theta by dt is equal to angular velocity omega, where theta is the angular displacement. Rate of change of angular displacement with respect to time is angular velocity. So VA is equal to r omega. Now again deriving the second derivative of the displacement will give you the acceleration. So d square SA by dt square will be the acceleration. So I am finding the derivative of this one again. So r into d square theta by dt square. So but d square theta by dt square is not in the curvilinear motion. D square theta by dt square is the angular acceleration alpha. So this becomes r alpha. So acceleration, linear acceleration of the point A will be equal to r into alpha. This equation is already familiar to us. This is the relation between linear component of velocity, acceleration and all with the curvilinear component. So linear velocity V is equal to r theta, r omega, where V is the linear velocity, omega is the angular velocity, and A is equal to r alpha, where A is the linear acceleration and alpha is the angular acceleration. This equation already we have derived in the earlier parts and all. Now thus when the wheel rotates without slip, the relationship between the motion of its geometric center and its angular motion are SA equal to r theta, VA equal to r omega, A equal to r alpha. So these equations are we can use this equation to find the motion of the center of the rotation. Okay. So anyway, these equations are applicable to the general case also. This is just the relation connecting linear motion as well as the rotary motion. Now to solve the problems coming under this plane motion, we will be using a new technique, that is what is known as the instantaneous center. So we must be able to locate the instantaneous center. Then it is very easy to solve the problems coming under the plane motion. So I will describe you what is instantaneous center first. A general plane motion possesses both rotation and translation simultaneously. That I have already told. General plane motion is actually a combination of rotary motion as well as the translatory motion. This motion of rotation and translation at a given instant can be considered as that of pure rotation about an imaginary point. Okay. Actually, plane motion is a combination of rotary motion as well as the translatory motion. So I am considering an imaginary center of rotation, so that this both rotary as well as the translatory motion can be considered as a pure rotary motion about an imaginary center. Then that center is known as the instantaneous center. This point about which body can be assumed to be rotating at the given instant is called the instantaneous center of rotation. So for analyzing the problems and all, we are finding an imaginary center, so that the entire body is assumed to be rotating about that imaginary center. Such a point we will be identifying in each problem. For every instant this point will be different, this instantaneous center will be different, but anyway we will be able to identify some tricks are there that I will explain in the upcoming slides. So anyway, the definition of the instantaneous center is actually the plane motion is the combination of rotary motion as well as the translatory motion. But by assuming an imaginary center, we are converting that plane motion into a pure rotary motion about that imaginary center. Such as imaginary center is known as the instantaneous center. Now this point is not a fixed point, and when the body changes its position, the position of the instantaneous center also changes. See, it is specifically mentioned here, this is not a fixed point. For every instant we can find the instantaneous center for that particular instant, and for time by time it will be different. The instantaneous center is not going to be constant for all the time. The locus of the instantaneous center as the body goes on changing its position is called the center rod. That is not much important for us. Now we will move on to the topic how to locate the instantaneous center. Now I will explain the concept with a figure. What is instantaneous center? You can see this is a rigid body. When the this thick line shows a particular body, and each point of the body is having different velocity. See, the point P is having velocity Vp in this direction, and point A is having velocity Va in this direction, and point B is having velocity Vb in this direction. Okay. So far we have considered in the linear motion all the point will have the direction of the velocity of all the point will be same, and the rotary motion also the same thing is happening. But in the case of plane motion, the different point in the body will have different velocities in the different directions. So that is why it is called a combination of rotary motion as well as the translatory motion. So here the point P is having velocity in this direction, and the magnitude is Vp, and Vp is not equal to Va. Here A is having velocity Va along this direction. See, both direction and magnitude are different. See, this is a shorter vector, this is a larger vector, means this will have a larger velocity, and this is in this direction, and Vb along some other direction not parallel to all these things. So in that case, to find the instantaneous center, what we will do is we will be drawing perpendiculars to the from the end of the velocity vector to the direction of the velocity. See, the velocity at the point P is along this direction Vp. This is a vector shown here. So I am drawing a dotted line here perpendicular to this velocity vector Vp. So I will draw a dotted line perpendicular to Vp. Similarly, the velocity vector Va is along this direction, and I am drawing a perpendicular 90-degree line, dotted line perpendicular to this Va. Similarly, from Vb, for the Vb vector also I am drawing a perpendicular from the end B. So from point P I am drawing a perpendicular to vector Vp. From A I am drawing a perpendicular to velocity vector Va. From point B also I am drawing the perpendicular. So all these lines will meet at a particular point. Then we can say that all these points are rotating about this particular point C. Now this center is the instantaneous center. So if you want to find the instantaneous center, then you take at least two velocity, identify two velocity, direction and magnitude of the two velocities of the different points of a particular body. Then you draw the perpendicular to that velocity vector. The meeting point will be the instantaneous center. That is the method to identify the instantaneous center. I think the concept is clear for you. Now this is the terms explaining how we have identified the instantaneous center that I have already explained. Now the angular velocity of the body omega can be determined as see, I am assumed that this entire body is rotating about this point C. See, this body will be rotating about this point C. Now the motion is converted into a pure rotation. Now if you want to find the angular velocity omega, now the angular velocity omega can be determined as omega equal to, from the definition, earlier definition, we have seen that V is equal to R omega. That is the general equation. V is equal to R omega. This is the equation connecting velocity and the linear velocity and the angular velocity. Here, since I have assumed this as the center of rotation, so with respect to this point A, the velocity, tangential velocity is Va, and this is the distance to the tangent. So actually I can take this distance as the radius. For this point, this distance will be the radius. So here the R for the point A, radius of the rotation for the point A is Ca, and here the radius will be actually it's not Ca. If I am taking this point as I is the notation for instantaneous center. So Ia is the radius for the point A, and Ib is the radius of rotation for the point B, and Va, Vb are the linear tangential velocities. This is very important. The velocity considered should be tangential. Actually, to Va we are drawing this as perpendicular, so that means to this radius this is tangential. So that is satisfied here. So we have the relation between the linear velocity and angular velocity as V is equal to R omega. So omega equal to V by R. So if you talk about the velocity Va, if you want to find the angular velocity omega, then omega will be equal to V by R. Actually, velocity at point A is Va, and the radius of this rotation from the instantaneous center to point A is Ia. So Va by Ia. Similarly, similarly for the velocity, if you want to find the velocity of P, then Vp will be equal to R omega. Here R is Ip. Ip will be the radius of rotation. So Ip into omega will be the velocity of the point P. So somehow if you are able to identify the omega with the known velocities and instantaneous center, then if you want to find out the velocity of some other points, then you can go for this equation. Okay, Vp is equal to omega into Ip. See, actually I can identify the instantaneous center with Va and Vb alone. If Va and Vb is known, I am drawing the perpendicular to both, then the instantaneous center will be this one. Now I can join a line from I to P. So Ip will be the radius for this velocity Vp. Or if you draw Ip, then if you draw a perpendicular line, then that will be the direction of the velocity of Vp. Everything is possible. You can take it in the reverse order also. So that is the method to identify the instantaneous center. Now some possibilities are here. In this example, you have considered all the velocities are in different directions, so nothing is parallel. So there won't be any problem of all. We will definitely have some point of common intersection, so that is the instantaneous center. But always the problems won't be like this. You can see in this case, the case A, you can see Va is the actually direction and magnitude of the linear velocity at point A, and Vb is the direction and magnitude of the linear velocity at point B. You can see Va is greater than Vb, and unfortunately these two velocity vectors are parallel to each other. So if you draw the perpendicular, see as per the earlier discussion, to identify the instantaneous center, what we have to do is, from A I have to draw a perpendicular to Va, from B also I am drawing a perpendicular to Vb. The meeting point will be the instantaneous center. That is what is we told. But here if you draw the perpendicular, you can see both will be going along a straight line. So if two velocity vectors are parallel, then we cannot find an intersecting point. In that case, what we will do is, we will draw the velocity at two known points with magnitude. So Va is actually drawn as a vector with same scale. So if it is 3, then I will take it as 3 centimeter. If it is 2 parallel to this Va, I will draw Vb parallel to Va, but the scale is 2 centimeter since it is 2 meter per second. So from the end point, joining the end point, I will be drawing a line, dot line, you can see here, joining the both end point of the velocity vector, and at the same time AB is joined. I am drawing a dot line joining A and B from the other end of the velocity vector. through the end point of the velocity vector I will be drawing a dot line. See, the both line will be meeting at the instantaneous. Then this point is the instantaneous center I. So the method you have to follow is, first draw the velocity vector in magnitude and direction through the known points, and draw a line joining the both endpoints A and B. Now through the end of the velocity vector you can draw a line. Now these two lines will be meeting at a particular point. That point will be the instantaneous center. If assume that if VB is greater than VA, what happens? VB is greater than VA, then instantaneous center will be coming in this side. That's all. The method will be same. You draw a line connecting B and A, then from the end of the B and through end of the point A, VA, join a line and extend it to meet at the line drawn from B and A. So that is the only difference. Sometimes the velocity vectors can be parallel, but the direction will be different, as shown in the case B. Here you can see the direction of VB is in this direction, and the velocity vector at A is opposite to the velocity vector at V. Both are parallel but in the opposite direction. In that case, what you will do is, you just draw a line joining A and B. Now from the both end of the velocity vector you can draw a line joining both end of the velocity vector. This will be crossing the initial line drawn through the B and A at this point. Then this will be the instantaneous center. So if the velocity vectors are parallel and in opposite, then in that case you have to join both end of the point where the velocity is considered, and from the extreme end or the end point of the velocity vector you can draw a line joining the velocity vector ends. Then the crossing line will be the instantaneous center. Okay. Now as a special case, you can see the figure C here. VA and VB both are same in magnitude as well as parallel. Then what happens is, if you join AB, then you will get a line through the extreme ends of the velocity vector. I am drawing a separate line. So there is no chance for these two lines to meet, since both are parallel. This distance is equal to this one. That means both will be parallel. In that case, the instantaneous center will be at the infinity, or we cannot find an instantaneous center for this one. That is all about locating the instantaneous center. Now one more important thing you have to note down is, these things are you are studying in the higher semesters and all. For mechanical students, mechanics of machinery is an important subject and one of the toughest subject. In that you will be dealing all these things. So you can see, as a thumb rule you can take this slide. The following rules are applied for location of the instantaneous center I. First one is, the I should be located at the center of the turning pair. You can see this one is the turning pair. Actually a pair means two bodies in contact. That is what is known as the pair. Okay, if the movement of the one link, we can say it as link. So the movement of two link is actually two link in contact is known as the pair. And if the movement of one link is if one link is rotating about the motion of one link is rotary about the other link, then we will count as a turning pair. Okay, see here you can see link 1 is actually a joint here, link 2 is this one, this rod is link 2, and this one is the link 3, this rod is the link 3, and it is connected here. So this 3, if this 3 is rotating about this link 2, then we can say 2 and 3 constitutes a turning pair. So in the case of the turning pair, the instantaneous center will be at the center of the turning pair. See, the instantaneous center for the joint link 2 and 3 is this one. This is the joint for 2 and 3. So this will be the instantaneous center. And as far as link 2 and 1 and 2 is considered, this will be the instantaneous center. Now next one is sliding pair. If the motion of the one link is sliding with respect to the other link, then we will call it as sliding pair, just in the case of the piston cylinder arrangement. So piston will be moving inside the cylinder. So with respect to cylinder, the piston is sliding. So that types of motion are known as, that types of pair is known as sliding pair. See, this block is actually sliding over this horizontal surface. Actually this surface is stationary. So in this case, the I lies at infinity in the direction perpendicular to the path. See, the instantaneous center will be along this line. See, and also I can explain the same thing in a different manner. Since the block is moving along horizontal direction, so the velocity, linear velocity of this block will be along along this direction or horizontal. So the instantaneous center will be on a line joining on a line which is drawn perpendicular to the velocity vector. So velocity vector is actually horizontal. So a line drawn perpendicular means that line will be perpendicular to the horizontal, that is along this y direction. So along this line only instantaneous center will be there. If you can find some other velocity and if you draw the perpendicular line to that velocity, then the meeting point will be the instantaneous center. Now the third one is the rolling pair. So rolling pair means one pair will be always rolling with respect to the other pair. See here, this is stationary, surface is stationary, and assume this is a wheel and this will be rolling over this surface. So that is what is known as the rolling pair. The motion of one pair with respect to the other is rolling, then it is known as the rolling pair. So the instantaneous center of the rolling pair is always the point of contact between these two pairs. See, during this motion, the point of contact is at this point. So this point is actually the instantaneous center between this 1 and 2. As far as 1 and 2 is considered, this is the instantaneous center. Okay, if the number of links are more than 2, then it will be very difficult to apply all these rules. Anyway, the common rule is you somehow identify the velocity, direction and magnitude of the velocity at least two different points of the body. Then draw the perpendicular lines to that velocity vector. The meeting point will be the instantaneous center. Okay, that is all about instantaneous center. Once you locate the instantaneous center, then it is very easy to find the linear velocity and angular velocity using these equations. You can see omega equal to Va by the distance from the instantaneous center to that particular point A. Okay, by that way you can identify the omega. Va is known to us, and once you locate the instantaneous center, then the distance from the instantaneous center to that particular point where we know the velocity is also we can measure. So that once we got that distance means you just divide that linear velocity with that distance, then you will get omega. Once you got omega, then if you want to find the velocity of some other point which is not known to us, then what we will do is we will be identifying the distance from the instantaneous center to the point where we want to find the linear velocity. That distance we will identify. Then we will multiply that instant with the angular velocity, then you will get the linear velocity at that point. Okay, that is the common method. For the why we can apply this equation is, for a rotary motion always the angular velocity remains constant. Omega will be equal for all the points. That is the basic of using this equation to identify the linear velocity at any point. Okay, I think the concept is clear for you. Now in the next presentation we will be seeing the problem related to all this.